Good morning, everybody. Welcome to the latest edition of the Pangolin Seminar. Today, Merlin from Aachen University will be speaking to us about the relation between the universal Teichmuller space and anti-de Sitter geometry. So, over to you, Louis.
All right, thank you. Let me just share my screen. All right, can you see it?
Yes, yes.
Okay, well, thanks, and hi everyone. Welcome in Paris. Yeah, before I start, I really would like to thank you for the invitation. It's a great opportunity to speak, and in fact, it's the first time that I speak about this project. So it's also nice to hear about your feedback, and also thank you for organizing the online seminar. It's great that we can keep such meetings, actually, because I don't know about you, but I miss a lot our weekly seminars here and there, and well, I miss it a little less with the online possibilities. So thanks a lot for that, for keeping us busy and connected. All right, so what I want to do is to report and to do an extended report on the paper that we wrote together with Jean-Marc Schlenker in Luxembourg, where we are supposed to study connections between the universal Teichmuller space and ADS geometry, ADS tree space. And what I mean by extended report is that I don't want to jump too fast to the main point, which will only appear in section 3 there. But before that, I want to spend some time explaining what is ADS geometry, and also, since it's about universal Teichmuller, maybe it's fair if I also spend some time discussing the relation between the actual Teichmuller space and ADS tree space. This, by the way, is mostly contained in the work of Mess, and I will explain this relation there. And also, one of the points that I'm trying to make is to explain why there's a real interest to go from the Teichmuller to the universal Teichmuller. So I will also spend some time discussing the motivations behind our main work, our main survey. Right. So let's talk about ADS tree space. So it's as we will see, it's a Lorentzian manifold, very much related to the hyperbolic tree space. And well, one of the first similarity with hyperbolic space, that it also has different incarnations, and I will present two of them. One is the Lie group model, maybe related to the hyperboloid model of the hyperbolic tree space, and the projective model. The projective model is closest to the Klein model of hyperbolic geometry. And so here it is. ADS tree space is as a manifold. It's the Lie group PSL2R. It's a Lie group, so in particular it's a manifold. And we're going to put a metric on PSL2R by first defining the metric on the tangent space of identity of PSL2R, which is called the Lie algebra. And this metric at the identity is the killing form, and then we push this metric all over the manifold by the action of PSL2R on itself, right? And it's not quite the metric that we are defining. There is a constant one ace there, but actually never mind about this constant one ace. It's just made in such a way that the curvature is actually precisely -1, so that it's even closer to the hyperbolic space. But I will not really discuss the differential geometry of the ADS3 space. So let's say that the metric is almost the killing form, right? And yeah, I use the word metric for this killing form, which might be a little bit abusive because it's not a Riemannian metric. It's Lorentzian metric, meaning there's a two positive direction, one negative direction, and yeah, it's not surprising, right? Because say PSL2R is isomorphic as a group to PO21, or maybe just the connected components of PO21. So it's kind of natural that PSL2R preserves a Lorentzian form. And in this context, Lorentzian context, or even pseudo-Riemannian context, it's quite classical to assign a type to tangent vectors, and the name of those types is based on, say, theoretical physics. So there's a vector which are space-like if the norm is positive, time-like if the norm is negative, and light-like if the norm is vanishing. So that's the Lie group model, and now we are going to reconstruct all over again the ADS3 space, just for the point to be able to embed it in the projective space, actually. So this time I'm going to be a little bit more explicit about this killing form. So the killing form is the restriction to minus determinant on SL2R. So the determinant is a quadratic form on M2R of signature 2,2. And if I restrict to SL2R, I lose negative direction, so the signature becomes 2,1. And it's not really hard to show that it's actually the killing form. And now we see the projectivization, right? It's just going from SL2 to PSL2. And now the ADS3 space appears really as an open set of RP3, right? The quadratic form also descends to the projective space because in dimension 2, determinant of A equals determinant of minus A. So we can recall this quadratic form downstairs on the projective space. And so what is the outcome of this reconstruction? What is the gain? What's the gain? Well, to see ADS inside RP3 allows to define both a boundary. Sometimes it's called the boundary at infinity, but it's not really at infinity, because I could reach the boundary by following a light geodesic. So I could reach the boundary at distance 0. So I don't really want to call it boundary at infinity. And also I get what is called a time orientation, meaning a well-defined future and past all over the manifold. And this I want to explain in the picture. Also, yeah, I feel like I should apologize for the picture because it's really ugly. But let's see if we can agree on the meaning of this. So yeah, so this is a picture first. This is a picture in the affine space. So this is an affine chart of ADS3. And see, so in the ADS3 is the inside of the quadric defined by Q. So if I wanna compactify, I should just maybe add the locus, which is the boundary of the boundary in the projective sense of this inside of a quadric, which is equivalent to say that I wanna put the locus Q equals 0 and add it to the ADS3 space. And I also get a time orientation. So let's say at this point X, inside the tangent space, there is two connected components of a time-like vector. So by the way, I drew this. I drew this is the green geodesic right there is of time type, and it's actually closed in this top and bottom disks are at infinity in the affine space, and they are the same in the projectivization, so that the ADS3 space is actually a solid torus, and the boundary is really a torus. And so in the tangent space at X, there is two connected components of time-like vectors. One connected component, I want to call it the future, and the other one I want to call it the past. And the thing is, even though ADS is not simply connected, I can do that consistently all over the manifold. Okay. And yeah, so here in blue, there is a space-like surface, and the red cone is the cone of light-like vectors, right? And also maybe funny remark, if say, you know, so this is PSL2R, right? And PSL2R is also the isometry group of H2. And in the isometry group of H2, there is also 3 types of isometries, right? Depending on the dynamic. There's the loxodromic elements, the parabolic elements, and the elliptic elements. And it turns out that this trichotomy is related to the trichotomy of space, time, and light, in the sense that if say if the X here is if I choose the affine chart so that X is the identity, and if I can connect, say, a point by if I can connect a point to the identity by a space-like geodesic, this point is going to be loxodromic in the isometry sense. If I can connect a point with a light like geodesic, this point is going to be parabolic. And if I can connect it by a time-like geodesic, the point is going to be elliptic, right? Those things are really the same. Okay, and finally, the isometry group of ADS3 is the group PSL2 cross PSL2. And if you want to understand this this isomorphism, you need to let act PSL2 cross PSL2 on PSL2, which is ADS3, right? Both by a left and right multiplication. So that gives you a morphism from PSL2 cross PSL2 to the isomorphism of ADS3, and you can show that this morphism is actually isomorphism. And last remark is that this isometry group kind of forces the boundary to carry an additional structure, which is also Lorentzian, so that the group can act conformally on the boundary. Again, very much like the conformal structure on the boundary sphere of the hyperbolic 3 space. Okay, so this I can also talk for the boundary of those 3 types, right? The space, time, and like also exist on the boundary. Okay, so that's it about ADS3 space, and now what I want to do, I want to construct manifolds which are locally ADS3. So now I wanna see this space ADS3 as a local model, and explain how do we construct a geometric manifold model on this ADS3 model. And this construction is the following, and it's very much related to Teichmuller theory. So Teichmuller space is this, right? It's the say of a closed surface. Teichmuller space is the space of discrete and phaseful morphisms from the fundamental group of the surface into PSL2R, and that's the same as assigning to the surface hyperbolic structure, right? The hyperbolic structure would be just H2 mod out by rho of gamma. And we say that 2 hyperbolic structures are the same if they are isometric. And at the level of morphism, it's the same as saying that the morphisms are globally conjugated by a single element of PSL2. So really, Teichmuller space is more like the quotient of this morphism space by this identification. Right, so that's at the level of surfaces, and now I want to embed this Teichmuller space into a space of representation in ADS3, or in the isometric group of ADS3. And to do that, I can take a point in the Teichmuller space, which is a morphism here, and compose it, post-composite, right, by the diagonal embedding of PSL2 inside the PSL2 cross PSL2. That gives you a representation of the fundamental group of the surface into the isometric group of ADS3. And this sort of representation is called Fuchsian. And as it turns out, this kind of construction is very flexible. So at this stage, a Fuchsian representation is just a copy of the 2 same representation into PSL2, and I can start deforming this guy, this rho, by considering not a single representation twice, but really two different representations, rho minus and rho plus, also discrete and faithful. So that I have now a different class of representation, and this representation will be called quasi-Fuchsian for the reason I will explain. And before that, let's see what is happening geometrically. Say let's do the parallel of this algebraic story in the geometric context. So at time 0, when I didn't start the deforming, the Fuchsian representation preserves a plane which is isometric to H2, and in particular it preserves also the boundary of this plane, which is a circle, a nice circle at this point. And if I start deforming, and do really something quasi-function, well, the group gamma is going to preserve something which is also topologically a circle in the boundary of ADS, but even if topologically a circle, could be geometrically really more complicated, and this thing is called quasi-circle. I will define it precisely in a second. And if I really want to get say a geometric manifold model on ADS3, what I can do, I can take the convex hull of this quasi-circle, and the group gamma through the representation rho minus rho plus acts on this convex hull, and the quotient is typically one of the manifold I want to consider. Call that a quasi-function manifold. So it's the quotient by gamma of the convex hull of the preserved quasi-circle on the boundary. Okay, so, and yeah, before I move on, let me describe really what is this object that we saw appearing in the boundary of ADS, this quasi-circle. So yeah, it's about, yeah, you will hear a lot the word quasi, maybe because the quasi-circle is formally the boundary value of a quasi-conformal diffeomorphism. So let me say what is quasi-conformal. So you have a diffeomorphism of the disk, and the disk is endowed with the hyperbolic metric. And if you take the pullback of the hyperbolic metric, it's again a Riemannian metric. So say at the point x in the tangent space of x, the unit circle of this new metric f star IP is an ellipse, right? And this ellipse, you want to squeeze it the best way that you can between two unit between two circles. I mean, you wanna yeah, squeeze it between two unit circles of rescaled hyperbolic metric. So you wanna rescale your hyperbolic metric by a factor c and by a factor kc. K here should be the best that you could, and you squeeze the ellipse, which is the unit ball of f star ellipse between the two disks. And of course, at any point you can do that, and you find the best k, which is the ratio of the big by the small disk there. But it's not always true that you can do that all over the disk, right? Because the disk is the disk is open, so this constant k might blow up. And if it does not blow up, if it stays bounded by k, you call the diffeomorphism quasi-conformal, at least, or even k quasi-conformal, just to remind the constant k. Right, and it's a fact that this sort of diffeomorphism, quasi-conformal diffeomorphism, extend to the boundary, and the boundary value, you call that quasi-symmetric homeomorphism of the disk. And this object that we saw right there in the middle picture is say, so the boundary is a torus, right? So it's a RP1 cross RP1. So this thing right there is the graph of some quasi-symmetric homeomorphism of the circle of RP1, right? And yeah, I also want to say that the quasi-symmetric homeomorphism of RP1 is quasi-symmetric in a much more naive sense, actually, in the sense that it does not distort too much the cross ratio. So the cross ratio is this number over there. It's a very natural number in RP1. It's the only projective invariant for 4 points in RP1. And here what I mean by RP1 is really R union infinity, right? So this C minus A, for instance, is the distance in R, or R union infinity between A and C. And we say that 4 points on RP1 are symmetric if the cross ratio is exactly -1. Okay, and you can show that quasi-symmetry, meaning being the boundary value of a quasi-conformal diffeomorphism, is the same as this bound there, that if you started with 4 points in a symmetric position, if you take the image by a quasi-symmetric homeomorphism, the cross ratio stays bounded. And so also the bound K prime there is not the same K as the K of the K quasi-conformality, right? But those two are related. In particular, that if K goes to infinity, if and only if K prime goes to infinity. So you lose quasi-symmetry in the sense of the boundary value of a quasi-conformal diffeo, if and only if you lose quasi-symmetry for this characterization. Right, so that's it about quasi-circle. Let me just point out that in the previous construction of quasi-Fuchsian manifold, the quasi-circle in the boundary has two additional properties. And first, it's achronal, meaning that you cannot connect any 2 points on the quasi-circle by a time-like geodesic. Actually, it wouldn't be a quasi-circle if you could. And it's also equivalent with respect to the two Teichmuller representation of rho minus and rho plus. Okay. And well, okay. So maybe you could think that this construction of quasi-Fuchsian manifold is very narrow, very anecdotic. And the point
sorry, Louis, just to interrupt you. So just to be absolutely clear, then, a quasi-circle is a graph of a quasi-symmetric function.
Yeah.
I don't think you said that explicitly, so I think it's good to.
Yeah. Thank you. That's exactly what I mean by quasi-circle. Exactly this: a graph in RP1 cross RP1, which is the boundary of ADS3, of a quasi-symmetric homeomorphism of the circle.
Thanks.
Okay, so the point of this theorem by Mess is to argue that the quasi-Fuchsian manifolds are actually frequent or even generic if you want to assume that the ADS manifold you try to construct contains a Cauchy surface. See, I think Mess is motivated by theoretical physics, right? You wanna say classify the manifold, which could be say modelization of our universe, or say possible solutions of Einstein equations, and Cauchy. So even though there is a dimension problem, right? Because our universe is our space time universe is 4-dimensional, and the ADS3 manifold are only 3-dimensional. So it's maybe just a toy model for describing the universe. But yeah, never mind. So this Cauchy surface, I think it's supposed to be the state of our universe exactly now, say at a given time, right? And in particular, it's space-like because it's supposed to be our environment, right? And it's also required to be a little bit more than that, in the sense that in the ADS manifold that MES wants to consider, every point in the past should be a cause in the state of our universe right now. So every point in the past should be in some sense visible as a consequence now, right? And also every point in the future should be a consequence of the state of the universe that we live in right now, right? So in geometrical terms, that means that every point in the manifold should be connected to the Cauchy surface by a time-like geodesic, right? And those kind of manifolds are called globally hyperbolic. Just means that they contain a Cauchy surface. And also MES add the hypothesis of maximality because it's supposed to replace an hypothesis on completeness, maybe, because it's really hard to construct ADS3 manifold which are complete, and instead of that, MES consider maximally globally hyperbolic manifold, meaning just that it's a globally hyperbolic in the sense that it has a Cauchy surface and it's maximal just for inclusion. And indeed, right? I mean, it's really, I mean, if you can travel in time, at some point in the time, you can meet a Big Bang and you lose completeness, right? So that's also kind of the thing related to physics. Although it's complete in the space direction. And the theorem of MES is that the construction that we saw earlier of quasi-Fuchsian manifold is providing absolutely all and exactly all the MGH manifold, maximally globally hyperbolic. So the conclusion is that, at least for theoretical physics, the quasi-Fuchsian manifolds are all we need. Okay. And now I want to introduce a last piece of structure for this quasi-Fuchsian manifold, and this structure we will see appearing at the boundary of the convex hull of the quasi-circle. So just as a side remark, the maximal manifold are not the convex hull of the quasi-circle, right? They are usually bigger, and the convex hull is not the maximal manifold. But still, there's something nice appearing at the boundary of the convex hull, and this nice structure is geodesic lamination, and I want to explain that. So the boundary of this convex hull of a quasi-circle is made by two surfaces, right? One in the future, one in the past, and those two surfaces are isometric to the hyperbolic disk, and so that we get two embeddings from H2 ADS3 and to the boundary of the convex hull. And the geodesic lamination is supposed to describe how those two H2 embed in ADS. And this embedding we will really encode with geodesic lamination, and actually even measure geodesic lamination. So how is this working? It turns out that this embedding is actually not strictly convex, or not in general strictly convex. And the locus of strict convexity is a lamination, meaning it's a union of complete hyperbolic geodesics, right? So a quasi-circle comes with those two geodesic lamination, two because one in the bottom, one in the top, or one in the past, one in the future. And it comes with actually more than just that, because you can also, you want to also keep track of the intensity of the pleating. So there's those geodesic lamination are the locus where those two surfaces are, we say, pleated, they are bent, right? And you want to keep track if the bending is more like smooth like this, or more intense like this. And this we will get it by considering a transverse measure on the lamination, which is the locus of pleating. Okay, so all adds up. The embeddings are described by this data, two set of data: a geodesic lamination, which is it's a closed subset of H2 made as a union of complete geodesics, and transversally to this geodesic lamination, there's a measure, and the measure is telling you how much did you bend along the geodesic, right? And this really is a transverse measure. Okay, and and also for the quasi-fuction construction, you could consider the geodesic lamination like living on a closed surface, right? Because everything is compactly periodic by the group action. Okay, and the theorem of Bonsanti and Schlenker right there is kind of a converse to this construction, in the sense that if you started with two measured geodesic lamination on closed surfaces, you could reconstruct them as the pleating lamination on the boundary of a convex hull of a quasi-circle, so that you can find a quasi-circle in the boundary of ADS, such that its convex hull has two boundary surfaces pleated exactly along the two geodesic lamination or measured geodesic laminations that you started with.
Did they prove uniqueness?
No, there is no uniqueness. That's what I meant by a partial converse, because you don't know uniqueness in this statement, and okay. it's still open actually. And so if I wanted to recap, we saw three different kind of object: MGH manifold, which by the theorem of mass is the same as the quasi-fuction construction of ADS structures, and a quasi-fuction manifold comes with two pleated lamination, and there's also a partial converse, because you could go the other way from fleeting lamination to quasi-fuction, but then we don't know uniqueness. Okay, so far?
Yeah.
Okay. And now comes the universal Teichmuller space. And the bottom line is that we are going now to remove the algebra behind this construction. So we are going to consider exactly the same kind of objects that we saw in the quasi-fuction construction, the quasi-circles and the pleating lamination, but we are going to forget that they come from a representation of surface group. And so the universal Teichmuller space is just the space of quasi-symmetric homeomorphism of the circle, but this time not necessarily nor invariant nor equivariant by a group representation or two. And yes, it is universal because it contains all the Teichmuller spaces for all closed surfaces. And I think one of the way to see that is if you say you fix a point in the Teichmuller space, which is a hyperbolic structure, you consider the conformal class of this hyperbolic structure, and if you have another one, you can relate the two conformal structures by a quasi-conformal map. And this map between the two surfaces is going to lift to the universal cover and extends to the boundary as a quasi-symmetric homeomorphism, so that you can embed the Teichmuller space into the universal Teichmuller space. Okay, and the main result that I want to discuss today is this one. So of course it should be an echo to the theorem of Bonsanti and Schlenker that we saw earlier. This time I consider a pair of measured geodesic lamination, this time on the disk and not on closed surfaces, and I wanna find a quasi-circle which allows to reconstruct the pair of lamination in the sense that the boundary of its convex hull is pleated exactly along the given lamination that we started with. And so there's hypothesis, bounded and strongly filling. Bounded just means that if you take a curve of bounded length, it will have a measure given by any of the two lamination, which is also bounded. So which is natural, right? Because you don't want to bend the surfaces too much. Well, actually, I will explain what happens if you bend too much. But as we will see, the object that we get is not going to be a quasi circle anymore if the lamination is unbounded. And the other hypothesis of strong filling is actually it's a little bit more debatable in the sense that it's not absolutely necessary. And if I can spare some time, I will comment on this hypothesis and maybe show you that it's kind of hard to find a necessary condition, but this one is absolutely not necessary.
Hang on, Louis. Excuse me, Louis. Thierry has a question, I believe.
Yeah, let me see.
Yes, I would like to. Is it possible when you have such a pair of bonded and strongly filling measured laminations on the disk Is it possible that one of them is filling entirely the disk, but the union of leaf is the entire apparent space, for example? You see what I mean?
Yeah, I think it's possible. Yeah. So you say the support of the lamin of one of the two lamination is
Yes, yes.
entirely H2. Yeah, it's possible. Yeah, it's possible. Again, if I can get to the last point, I have examples.
I have a related question. But if the geodesic is if gamma is a curve containing the geodesic of the lamination, then I think we should mean that the lambda minus, for instance, of gamma is 0, right?
Yeah.
I don't see how a simple lamination can.
Yeah, of course. You want to, you can only measure transverse curves to the lamination. So, yeah, I think you're right. You can declare that the value of let's you can declare that the value of say lambda minus to a geodesic containing lambda minus is 0, right?
In fact, if one lamination is empty, then I don't think that you can have another lamination that fills unless it's empty itself, right? That sorry, not the fills that is realized on the boundary of unless it's the trivial lamination itself.
Yeah, exactly. No, I'm not sure. Yeah. I don't think it's possible to have one of the two lamination which is empty. Yeah, one could be the one full support, but yeah. Okay, did I answer or?
For me, yes. I don't know about you.
I think it's good.
Yes. We have too much interfered. Maybe after.
No, that's fine. Okay, so boundedness and strong feeling, and let's see if we can discuss strong feeling at the end. Okay, and yeah, of course, I want to give you some ideas about the proof, but before I proceed to the proof, I want to give you some motivations, and I want to take you through actually two motivations. One is related to earthquakes, and the other one is related to what is called Weil's problem. So earthquake is this: if you have a geodesic lamination, you can do the following thing to define a map from H2 to itself. And what you do is you cut. So say, for simplicity, say the lamination is every leaf is every geodesic is isolated, right? Because it's every lamination is actually a limit of laminations with isolated leaves. So let's define just earthquakes from this simpler lamination, and the general procedure would be actually a limiting process. So you cut H2 along each leaf of the lamination, along each geodesic of the lamination, and if you want to define the left earthquake, you slide the left half plane, which is on the left of lambda, by a distance corresponding to the weight of the leaf. So in the case of laminations with isolated leaf, every geodesic comes with a Dirac mass, right, which is the transverse measure. And this Dirac mass has a weight, and you use this weight to slide the left part of H2 by such a distance. And then you glue everything back on. So this is earthquake on H2, and indeed, I mean, this is very harsh, right? I mean, it's not continuous, and it's discontinuous along its geodesic lamination. But and you could also do the same by the right, okay? And this would define a right earthquake. But what Thurston showed is that this sort of map, this sort of earthquakes, extend to the boundary in something which is a little bit more regular and in fact quasi-symmetric. And by doing so, we can by extending to the boundary, we can define this this earthquake map, this curly E there, as being defined on the universal Teichmuller spaces. So if you take a lamination and a quasi-symmetric OMIO, you compose the earthquake extended to the boundary by the quasi-symmetric OMIO. Right? It gives you a map from the universal Teichmuller space to itself. And actually, a complete restatement, a complete direct restatement of the main theorem is this result, is that if you take a pair of bounded and strong filling lamination, you can find a quasi-symmetric OMEO for which sliding on the left by lambda minus is the same as sliding on the right by lambda plus. And this thing was actually conjectured by Thurston, and I believe that the idea is that this sort of property never holds for dent twists, actually. And so, in a way, I mean, earthquake is kind of shows new dynamical phenomena on the Teichmuller space. That's kind of the idea of this statement. New meaning different to dent twisting.
Excuse me.
Yeah.
What is the statement that Thurston proved about these earthquakes? He proved an earthquake theorem for the hyperbolic plane.
Yeah, I think the earthquake theorem by Thurston that you can, if you, or even on a surface, if you take 2 points in the Teichmuller space, they are always related by an earthquake. You can find an earthquake, you can find a lamination such that the earthquake, say left earthquake along this lamination takes the one hyperbolic structure to the other one.
Yeah, this is for surfaces, for compact surfaces.
This is for compact surfaces, yeah.
But I guess Thurston did an earthquake theorem for the H2, for the universal Teichmuller space.
Oh, okay.
Yeah, Thurston proved that any homomorphism, any orientation preserving homomorphism of the circle is the boundary value of a unique earthquake map, in fact, of H2.
And maybe if it is a quasi-symmetric, then it is by a bonded lamination.
Exactly.
Yeah, bounded and being able to extend is equivalent. Okay, so this is more like this statement is more like a fixed point theorem, right? I mean, if you compose the left earthquake by the inverse of the right earthquake, it has a fixed point, and not a Thurston theorem is more like a transitive statement.
Oh yes, okay.
Okay, and on a different spirit, there's the main theorem is also connected to Weil's problem, and let me briefly describe what is Weil from it. It's actually a very rich and very long story, so let's just be sketchy. And the origin of Weil's problem is probably this result by Cauchy on the rigidity of convex polyhedra. It's actually attributed to Cauchy, but the proof was not correct until Legendre, I guess, fixed one of the part of the argument. So it's more like Cauchy-Legendre theorem. And the theorem states that if two convex polyhedra have the same faces, then they are the same, or they are one is a displacement from another. And say Weil's problem is an extension of this result, and it asks what kind of metric on the sphere you can realize as the boundary of a convex domain in say the Euclidean space or hyperbolic space, ADS, or I don't know, Minkowski, whatever. And also uniqueness. So that actually Cauchy theorem is belongs to this Weil's problem because it's the uniqueness statement for flat metrics, right, with singularities. And now, at least in the Euclidean and hyperbolic case, the Weil's problem is more or less completely understood by this result of Alexandrov for the Euclidean space and Alexandrov Pogorelov for the hyperbolic space, stating that every smooth metric with a natural condition on the curvature, this positive curvature in R3 and in curvature greater than -1 in H3 is absolutely necessary. So this is the natural condition somehow. Every smooth metric with this constraint on the curvature is realized as the boundary of a convex in R3 or H3, and this convex is also unique. And yeah, I believe there's also non-smooth versions of this result. So that's actually Cauchy's theorem is really a particular case of some version of this theorem of Alexandrov and Alexandrov-Pogorelov. So that's for metrics on the sphere, and in this case you want to find a bounded convex, but the more modern question should be about the unbounded convex sets. And in this case, it's not even easy to find a good statement, right? Because at least about uniqueness, because you could embed, say, H2 in H3 in many different ways. So uniqueness seems to be a little bit weird in this case, but it is believed that if you add some conditions on the behavior at infinity for this convex domain, you could have uniqueness. So in particular, this conjecture right there seems to be kind of plausible. I put it in a simple way because I'm trying to realize metrics only of constant curvature, but it's not absolutely necessary. But the conjecture is the following: if you consider two metrics of constant curvature on the disk, it should exist a quasi-circle so that the boundary of the convex hull of this quasi-circle is exactly isometric to G minus and G plus. And you could even try to ask about uniqueness, but it seems to be very more, say, challenging, the uniqueness. And so I put it ADS3 here, but you could also put H3. It's open also in the case of H3. And it turns out that if the curvature approaches -1, the surfaces of constant curvature become pleated surface. So that the version of this conjecture for k equal -1 is answered by our main theorem, right? So you can also see the main theorem as a modest contribution to Weiss's problem. Okay, so let's see about the proof briefly, maybe. Or yeah, can I take 5 minutes to do the proof, or is it over?
Yeah, definitely. So you've just run, your hour has just finished, but yeah, 5 minutes for the proof would be great.
Okay, I'll be quick. So the data is right there, right? You have a pair of measured lamination that you wanna realize as the pleating lamination of the boundary of the convex hull of a quasi-circle. And the proof goes like this. There is two steps. The first step is that first you wanna approximate your laminations lambda minus and lambda plus by what is called a polyhedral lamination. I will tell you what I mean. And then I want to argue that by doing this polyhedral approximation, I also get an approximation of the quasi-circle that I'm looking for. And this approximation of the quasi-circle takes the form of discrete quasi-circles, which I want to define. It's a funny little new notion, I believe, that we discovered along the way. Right. So let's do first polyhedral approximation. So this step is actually the most technical part of the proof. So I will be very, very brief. So in the first picture in the top left, there's the original lamination, that the one that we really want to reconstruct, right? So the red one is the one we want to put in the future. The blue one is the one we want to put in the past of the convex hull. So first, what I do is that I take a big ball of big radius r in the hyperbolic plane, and I remove every geodesic which does not enter this big ball. Okay, and then I want to argue that this new truncated lamination, I can realize them as polyhedral lamination, meaning I can find an ideal polyhedron. Ideal means that the vertices should be on the boundary of ADS3, and such that, so this polyhedron should have say what is called a Hamiltonian path on the vertices, which is a path that goes exactly once through all the vertices. That I want to call maybe the equator of the polyhedron, and so that the polyhedron has a future and a past components, and I want that the future components is pleated exactly along this truncated lamination in red, and the past component would be a pleated surface pleated along the truncated lamination in blue. And so this step is kind of, well, actually it's not really completely true. What I need to do is to actually delicately modify this truncated lamination so that it can actually be realized, but yeah, let's not be too precise. And I should also point out that this is the step where we use the strong filling hypothesis, right? Because this lamination, this pair of truncated lamination is realized if they strongly fill, and this is kind of visible. I mean, if you want to realize those lamination as polyhedral, you will see that, I mean, if you take a curve in the, say, in the polyhedron, if you count anytime you meet a geodesic, a pleating geodesic, if you count the weight of this geodesic and you add all the weight, you will see that a long curve, because this polyhedron closes up. If you take a long curve, the long curve is going to meet the lamination a lot, right? So strong filling is kind of necessary for this step of the construction, right? So if you believe this, let's say the outcome of this construction is an ideal polyhedron, and the vertices of this ideal polyhedron, I wanna see them as a discrete quasi-circle. And so a discrete quasi-circle should be the following thing. So of course, again, I would wish to define discrete quasi-circle as sending symmetric points to point of bounded cross ratio, but maybe I can't, right? Because if I take a finite set in RP1, maybe there is not a single four tuple of point which is symmetric. So I need to relax this condition a little bit, and I need to allow the point to be in a, say, almost symmetric position, and I want that point in an almost symmetric position would be taken to points of bounded cross ratio. And of course, one of the examples of such a thing is just the restriction to an actual quasi-symmetric homeomorphism to a finite set. That would be okay. And the theorem is actually some kind of a converse of this restriction example. The theorem is like a compactness argument, compactness result. So say the finite set is getting bigger and bigger, and it's getting eventually dense in RP1, in the sense that every point in RP1 can be approached by a point in the sequence of finite set, and also that the discrete quasi-symmetric are all quasi-symmetric, but for fixed constants, right? For fixed k, they are all k quasi-symmetric. Then, if I can find such a sequence, it will converge or subconverge to something which is actually a real actual quasi-circle, right? And I should mention that this theorem is it's kind of so this say it's reminds of a theorem by Alfors, which is the same for quasi-circle, right? There's a compactness theorem for quasi-circle for fixed k. So a sequence of k quasi-circle, in a sequence of k quasi-circle, you could extract a converging subsequence. And the last part of the argument should be, of course, checking those two hypotheses. So the first one would be actually given by the construction. So you would have to believe me that by doing such the polyhedral approximation, if you truncate the lambda minus and lambda plus less and less, meaning you cut it by a ball which is which is bigger and bigger, the vertices are going to fill the whole RP1. And for the second part, meaning checking that you can actually find a uniform constant K, so that all the discrete quasi-circle are K quasi-symmetric. It's based on a fact which is typical in ADS geometry, that you can actually precisely know when the constant of quasi-symmetry are going to diverge. And actually it can only happen one thing, and this thing is called a rhombus. And this is exactly what happens when a quasi-circle becomes less and less quasi-symmetric. So this is to describe. So at the boundaries there's 4 light-like lines. The red one, this, I don't know if you see the mouse, but there's four red curves in the boundary, which is well, it's not really a quasi-circle anymore, because the K constant has diverged. And inside ADS, there's 2 space-like lines. And just by a simple geometric argument in ADS, you will see that the dihedral angle of those 2 space-like line would be infinite in this case. So that's actually not possible if you started with a bounded pair of lamination. Actually, this picture explains also what happens if the non-bounded. So this cannot happen. So this quasi-symmetry constant cannot blow up, and we can apply the compactness argument for discrete quasi-circle, and we find the actual quasi-circle by as this limit of discrete quasi-circle. Okay, I think I'm out of time, so I should just maybe stop there. And thank you for your attention.
Thank you very much, Louis. Thank you very much. So everybody, please unmute your speakers. Oh, thank you very much, Louis. I think there are quite a few questions. Does anybody have any questions?
Yeah, I do have a question, if I can.
Yes, go for it, Andrea.
Sure.
In fact, I think I have more than one question, but I would like to first to ask one, just basic one. So if you have a pair of polyhedral laminations that are realized on the boundary of an ideal polyhedron, they don't strongly fill in your sense, right? Because if you draw 2 laminations, one on top of the other, I mean, there are gaps.
Yeah,
So
exactly. Yeah. No. Yeah. A finite lamination of a finite pair of lamination cannot strongly fill.
Yeah. So I think I don't understand something in your approximation procedure, because you start from a pair of strongly filling laminations, but they have to be somehow dense everywhere, right? I mean, in a very strong sense.
Yeah.
If you cut with a ball of finite radius, of a certain radius, then you don't find a finite lamination, right? Because you still have sort of dense.
Yeah.
The laminations are sort of dense in this ball of radius R. Am I wrong?
No. You're right. This remark that this truncated lamination, or this pair of truncated lamination don't strongly fill is correct. Yeah,
no, I mean, it's not
I didn't really describe this approximation.
So what I don't understand is that you cut with a ball of radius R, and then you sort of discretize the lamination in sense.
Yeah.
Okay. Just maybe I missed this step.
Yeah. Maybe I should ask just one more thing, is that this is based on results of Denzinger, Maloney, and Schlenker. where they describe very precisely the polyhedron that can be inscribed in a quadric. So yeah, we very much rely on this result, and I mean, they have a very neat and complete answer to this fact. You start with a graph, label graph, say, and the label on the edges, right? And you want to say that this graph is realizable as a polyhedra if and only if there's some condition on the labels actually. And this is typical. This is the thing we use, but yeah, it's a proof that I can do either in 5 minutes or in 30 minutes, but really not really in between, right? Because then I start saying something about this procedure, and it's getting complicated and.
No, that's fine. So even the simplest example I think I can think about is just take two totally basic planes that meet at an angle.
Yeah.
In this case, the top lamination is just one leaf with a certain weight.
Yeah.
And the bottom lamination is sort of dense everywhere.
Exactly.
So these two, they don't.
No, exactly. That was actually also one of the points that I was maybe willing to make, is that this does not strongly feel, and this is realizable, right? So the strong feeling condition is not absolutely necessary. Yeah, you're right.
Thanks. And very last question, which is maybe related to the comment of Thierry in chat, but never mind. I think if I were to try to prove this result, the first attempt I would have done would be to approximate the lamination by a sort of a sequence. I mean, approximate the pair of laminations by a sequence of pairs of laminations which are invariant by a certain function group.
Yeah.
Have you tried this? Is there a reason why this? And then you could use the theorem of Monsanto and Schlenker. So have you tried this before? Is there a reason why this does not work?
No, we never really tried this approach. Yeah. No, I don't know what to say. I mean,
that's fine. But I was curious if you tried the other one.
Yeah. No, not really. No, never thought about this, but it seems to be that it could be very hard to find this kind of approximation. But
can I just ask? It's maybe a silly comment, but I mean, there is a maximal radius of balls that you can put in compact hyperbolic surfaces.
No, but you have to let the genus go to become very large.
Oh yeah, silly me. Right, yeah, of course.
Co-compact.
Right, okay.
Okay, thanks for the answers.
Yeah.
So are there any other questions?
Well, additional comment, I understand that Andrea don't want to say that, but the approach that he was saying is what he has done with Francesco Bossante. But it was in the case of Minkowski, right, Andrea? That's the difference. It was not a pair-off, right?
You're muted.
Yes, you're muted, Andrea.
I muted myself. That's what I did. Okay. I think we also used this approach in ADS to prove that basically if you have a curve in the boundary of ADS, then you can find two case surfaces which are bounded by this curve. And in that case, we went through an approximation by the Fuchsian case. So we relied on the quasi-Fuchsian. So if we approximated the curve by a curve which is the graph or something equivariant with respect to two Fuchsian groups. And then I think we relied on your result, Thierry, about the existence of case surfaces for globally hyperbolic ADS manifolds. So yeah, that's why I had this in mind. But I think by these discrete cases also a very smart idea.
So you can approximate case surfaces by a periodic case surface. Right?
Yes, exactly. Yes. So in fact, the proof we had went the other way around. We approximate the circle, and then we know we have the invariant case surfaces, and then we go to the limit, showing that there exists the case surface in the general case.
Okay, cool.
Which paper is that, Andrea? Silent again. You are mute again.
I'm muted again, sorry.
Yes.
Do you hear it?
Yes,
sorry,
now I hear you.
I sent you the paper.
Oh,
I
please
don't
do.
know how this immediate reflection.
Yes,
Muting myself after I stopped talking. I sent you the paper. It's one about case surfaces in anti-de Sitter space.
Right. Okay. Excellent. Yeah, please do send me that paper. Are there any other questions? Well, if there are no other questions, I think.
Yes, that was
Oh,
one.
go ahead. Go ahead, Thierry. Go ahead.
My first question: what is RWTH University?
It's Aachen University, and to be honest, I speak so little German that I cannot even pronounce the. So no, let's try. Rheinine Technische. Yeah. No, it's just, let's say, the State University of Aachen.
Right. Okay. Excellent. Well, everybody.
Aachen is Aix-la-Chapelle in French.
Yeah, I forgot about that. It's a really nice city. Well, it's very pretty. It's got a nice cathedral. Very impressive cathedral.
Yeah. The theater center is quite nice. Yeah.
But I get the feeling there's not much to do there. I visited once. It's very nice, but not a place I want to live. Anyway, sorry about that. Anyway, everybody, please unmute your speakers and thank thank Louis once again. Thank you. Right, so I'm going to stop the recording now. Hang on, just.